بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Assalamu alaikum everyone. Today, our first lecture on control. Okay, so it's just in time. So you'll see that we're going to be looking at a number of control techniques. All of them actually, they're essentially just doing proportional and derivative control. You'll see how powerful PD control becomes, and if you reinterpret it this way, and how much can you do with it. And this, of course, will be the foundation of more advanced stuff that you can explore on your own, but this is really the basis of what we're going to be covering. We're going to wrap up the analysis part with another concept or another principle called Lassalle's invariance principle. So this will be an extension to the Lyapunov's direct method. So the recap, as usual, and then we're going to be looking at Lassalle's invariance principle. Then we're going to be looking at the PD control of a point mass. So we're just going to be looking at reinterpreting PD control in the simple Euclidean case. Next lecture, inshallah, will be where we try to do it on SO3 in a geometric way. So recap, so state space model. So we're looking at systems of this form. X dot is equal to f of x plus g of x u. And you have an output equation. It's the system, this state space model. And we focused on analyzing the equilibrium points of such systems. So we forget about the input u, and then we looked at x dot equal to f of x. And this f can either be the one without the u completely, so the open loop one. So you can forget about the inputs. You just assume the system is just naturally behaving. Or it could be the closed loop where you already chose a structure for the u and you plugged it in, and then this is what you're trying to analyze. We said that Lyapunov's direct method, if you have an equilibrium point under consideration you want to analyze, it can tell you whether this equilibrium point is stable, asymptotically stable, or globally asymptotically stable. If you can find such requirements, so these are the basic requirements that you need to find. You need to find the positive definite function, v of x, and its derivative along the system trajectory should be negative semi-definite. Then you can conclude the system is stable. Sorry, the equilibrium point is stable, which means that trajectories starting near it, they will not blow up, they will always remain near it. The trajectories will converge to that point, to that equilibrium point, if you can show that the point, the Lyapunov function is, the derivative of the Lyapunov function, v dot, is negative definite, not just semi-definite. And if you can also show in addition that the v of x, the original Lyapunov function, actually is radially unbounded, so it goes to infinity if you move everywhere away from the equilibrium point. Then you can show with that condition as well that you have global asymptotic stability. Then we looked at local definiteness. So how do we actually characterize whether a function is positive definite or negative definite? We found that a local way is actually using the Hessian, especially because the v of x itself, we can approximate it using Taylor series by a first zero order term, a first order term, and a second order term. So this is only a second order term. The first and the zero order terms, they just drop out because the equilibrium point that we're looking at is actually a critical zero, if you remember. And this is simply a basic result in a much bigger context called the Morse theory. Okay. How do we compute the v dot? So the v dot in general, okay, is given by this. We said it's actually given by this expression. This should be the other way around. So v dot is given by this expression. You take the pairing of dv of x with x dot, and we call the dv of x, we call it the differential of the function. So give me any function v, and I can compute what's known as the differential of that function. So dv of x is called the differential of the scalar function v, and dv of x is a covector in general, and this pairing is simply a pairing between a covector on and a vector for a given vector space. In the case of that this tangent vector, in the case that actually x itself is Rn, then the tangent vector to that Rn is another Rn. So you always think of, if x is Rn, then x dot is also another Rn. And simply this dv of x would be just you represent it like a column vector. And this pairing would be simply just you multiply by the column vector, the row vector multiplied by the column vector. So this would be a row vector, this would be a column vector, and this would be simply just the multiplication of both. But this generalizes to more stuff. And then we said that the x dot is equal to f of x. So this is actually how you just compute it. And also, this is something that I did not mention last time, but I just put it here on the slides for completeness. This is actually the definition of a more general operation, actually called the Lie derivative. So there's something that you might come across called the Lie derivative. So this is actually called the Lie derivative of the function v along the vector field sigma f. And this sigma f corresponds to the f, the dynamic equation, as we mentioned earlier. So this part, okay, is a little bit, on the side. Actually, it's called the Lie derivative. And actually, the Lie derivative is used in more stuff. Right? So something that we did not discuss at all here is controllability and observability. This is beyond the scope of the course. And actually, the Lie derivative is something that you use for that. Okay, so you use the Lie derivative in a recursive way to actually show controllability and observability. So but that's beyond scope. That's the case of Rn. So in the case, then you actually simply have, this is a 1 by n vector, and the x dot itself is given by f1, f2, f3, up to fn. And as we mentioned last time, you're actually familiar with this differential of the function. You're more familiar with this gradient vector. So if you give me any scalar function, then you're familiar with this gradient vector, which is the partial of the function with the partial derivative of the function with respect to x1, partial derivative of the function with respect to x2 up to xn. So we make this column vector, and then you simply would say that the v dot is this vector transpose with the x dot. Okay, but you see here that you're just mixing the nature of the two, these two objects. Okay, so this is in general this is a covector, and the x dot in general is a vector. Okay, and you simply have that these are just in Rn. This is the transpose of that one. Okay, simpler, but this is just a representation. This does not change the fact that actually it is naturally a covector. So this was the recap. So given a v, how do you show it's positive definite? Given a v dot, so how do you take that v and compute the v dot? And then you just check for positive definiteness, so you check for positive definiteness and negative definiteness of v and v dot respectively. Now we'll look at Lassalle's invariant principle, but before we look at how it is, let's see about what's the motivation behind it. Why do we need an extra result? Why is Lyapunov's direct method not enough? So if you usually what happens is the following. So the setting, if you remember that when we started with state space models, they were all of certain type. What type of systems we were looking at? No, I mean, what type of physical systems are we considering in the class? In a robotic sense. So what kind of, usually the equations of motion are of what nature? Like mass spring damper systems. And what do you call this class of systems? Mass spring damper. Sorry? Mechanical system, exactly. We're just looking at mechanical system. If you have a mechanical system, what's the first Lyapunov function or Lyapunov candidate that you always think about? Total energy, exactly, which is total potential energy and the total kinetic energy of the system, right? That's the first thing you would think about. So this is a natural Lyapunov function. This is a candidate that you have, and you can always evaluate whether it will decay. It will be less than or equal 0. Its derivative will be less than or equal 0 along the system trajectories. If you start by this way, you actually will find that usually that you will able to only show that v dot is negative semi-definite. Okay, you will even if you start with something as natural as just the total energy of the system, and you evaluate its evolution, you'll find that you can in many cases the best you can do actually is just negative semi-definiteness, and it's actually sometimes it's not easy to show strictly negative. And this is where Lassalle's invariance principle comes. It's an extension that says if you found the case where you found the Lyapunov function, it's positive definite, and you're able to show that its derivative is negative semi-definite, before giving up, we can actually do a little bit of more analysis, and we can show that the equilibrium point you're studying is actually asymptotically stable. Okay, so that's the whole idea, without changing the Lyapunov function. Okay, so before discussing what is the principle of Lassalle or this theorem that he came up with, we have to introduce a notion of an invariant set. What does an invariant set mean? So this is the general definition. So a set M is an invariant set for a dynamic system if every system trajectory which starts from a point in M remains in M for all future time. Make sense? Have you heard something like it? Does this ring a bell with something we already discussed?
Yes.
What? An equilibrium point, exactly. So you see that the equilibrium point is the point that you start at it, you remain at it, but that's only one point. What the invariant is a generalization of this. It's a bigger set of the state space, and you start in it and you remain in it. Okay? So that's the idea. Examples: equilibrium points. The domain of attraction of an equilibrium point. What is this idea of the domain of an attraction? So remember that we said that if we have an asymptotically stable equilibrium point, it means that if I start away from it, I go to that equilibrium point, right? If you take this bigger, part of the state space, exactly, you start in it, and what happens? You converge to the equilibrium point, but did you get outside of this domain of attraction? No, you stayed in it. So that's another example of an invariant set. Okay. A third example, which is actually trivial example, is the whole state space. You start in anywhere in the state space, you never exit out of it. So the first and the third example are actually trivial examples. Okay? The equilibrium point is a trivial example of a set which is a set that consists only of one point or multiple points. Okay? Because if you can have, you see here, this is with S. If you take the set of all of the equilibrium points, if you start at any one of these equilibrium points, you always stay at them. Okay? For example, the pendulum, you have the downward position and the upward position. So I have 2 points. Take them and make a set. Okay? So downward position, upward position. So that's a set of 2 points. If you start in that set, would you exit? No. So you stay in that set forever. So that's another example of, an invariant set. Is that clear? So it's just an easy extension, but we'll see how that works out for us. So now this is how the Lassalle's invariance principle goes. It says that let x star in the state space be an equilibrium point of the dynamical system given by this ordinary differential equation, x dot is equal to f of x and t. Assume that there exists a smooth Lyapunov function. So we have already found the Lyapunov function. And when we say here a smooth Lyapunov function, what does that imply? It's differentiable. What else? If we say it's C infinity, then it means it's infinitely differentiable. So that's already implied. What else? It's positive definite, exactly. When you say it's a smooth Lyapunov function, it already means that you've checked for the positive definite now. So it's already positive definite, such that in some neighborhood omega of x, that already includes the equilibrium point, you have that V is positive definite, V dot is negative semi-definite, and you have something else. So that's the extra condition now you see. You define a set R. So this set R is the set of all the points in omega that satisfy what? The derivative of the Lyapunov function you chose is equal to 0. So that's called the set R. Okay? So it's the set of points that the derivative of the Lyapunov function vanishes at them. Okay? Make sense? And then you let M, which is another subset of R, to be the largest invariant set in it. Okay? So you see the flow? We started by the state space, right? So this is where you define the V. And then we said inside of this whole state space, let's look at a slightly smaller set called omega. And this omega includes the equilibrium point you're thinking about. And inside of this omega, I'm looking at another smaller set called the R. And inside of this R, I'm looking at another smaller set called M. If you can show that M is the largest invariant set in it, then the theorem goes as follows. It says that if M contains only the equilibrium point that you want, so if inside of R, only the equilibrium point is inside of this M, if inside of R you find the largest invariant set, and this largest invariant set is only the equilibrium point you actually are interested in, then it is locally asymptotically stable. And not only that, you even have an estimation of its domain of attraction. And this is actually something, that Lyapunov theorem did not tell us about. You remember we said that we can prove that I'm locally asymptotically stable, which means that if I start near the equilibrium point, I can go to it. But we never characterized how big or small this domain of attraction is. With Lassalle's invariance principle, you do have a domain of attraction. What is this domain of attraction? So this is omega L. It is the set of all points in the omega such that v of x is strictly less than this number L. So L here is just a constant. It could be 2, it could be 3, it could be 5, just some number. So if I say omega 5, which means that this is the domain of attraction of the equilibrium point, it means that it's the set of all points that have their Lyapunov function less than 5.
And if it exceeds the number L, it will not converge?
So the L is part of the definition, you see? It's part of the definition of it. Okay? This is what you have a guarantee that if you start in it, you converge. Afterwards, you have no idea. At least with what the theorem says, I cannot say anything about it. You need more, different methods, different analysis, and so on and so forth. Okay?
Doctor,
Yes.
for the pendulum, the M is not included only the Y and Z.
Okay, you have to wait. Okay. Any questions abstractly before we go to the example? So abstractly, so this is this is actually this whole theorem. So the Lassalle's invariance principle is a little bit was stated differently. So how Lassalle proposed it, but then it was extended or reformulated with like a corollary of that theorem actually, and it's attributed to more people. So Barbashin and Krasovsky, okay, and Lassalle, okay, principle, okay. So this is what's on the slide here, okay. But people just say it, for short, it's Lassalle invariance principle. So again, just to summarize, you start by Lyapunov function, okay? You check its positive definite. You go calculate its derivative along the system trajectories. You find it is negative, semi-definite, exactly. If it's negative definite, you don't need all of this. If it's negative definite, then by Lyapunov theory itself, you already have a proof it's locally asymptotically stable. But the question is that if I check it's only negative semi-definite, and then instead of throwing this whole Lyapunov function and just trying to find something, another function which is not an easy task, then I can take the same Lyapunov function. I can where I stopped, which is negative semi-definite, and I can find the omega inside of it, and inside of the omega I find an R, inside of the R I find an M, and then I check. If the M has only the equilibrium point, then you have a proof that this equilibrium point is locally asymptotically stable.
How we decide the set M?
That's exactly what we're going to be doing in the example now, okay? Okay. So, just to answer that question abstractly, so the set M is the largest invariant set in this omega, in R. So large, what does an invariant set mean? Go back to the definition we just mentioned. You start at it, you remain at it. That's it. Okay? And largest here is not in terms of size, it's in terms of the union, for example. If I have set A and set B and set C, and each one of them is an invariant set, then the largest invariant set would be the union of all of these three together. So it's in terms of set theory, not in terms of big and small.
So set M can be the set R?
Set M can be, yeah, that's possible. If R itself, okay, is it's an invariant set, then okay, then it's R. I know it's not mentioned explicitly here. We don't have the equality, but yeah, I think you can easily add it. Okay.
Dr. M is the largest invariant set in R. And
in R.
Probably in omega as well.
R is in omega.
Yeah, because you just skipped this when you mentioned in omega, so you corrected yourself with.
I did that. No, so the picture is omega is in X.
Yes.
Okay, and then what actually defines omega? How do you choose omega in the first place? It's just a neighborhood that includes the equilibrium point. Okay, but by the way, and that's exactly what we're going to be doing in the example right now. It's not necessarily that I choose the whole state space, because the whole state space already includes the equilibrium point, right? And that's actually the whole idea. And I'll say it from now because we already started talking about it. What if that we reach this part and we find that M has the equilibrium point we want, but also other stuff? What do? We just throw away, we stop, or what can we do?
Maybe
What? Restrict the
area.
restrict the omega. Exactly. We can go a little bit smaller. We can make the omega a little bit smaller to maybe when we make it smaller, we actually exclude the other stuff inside of M. And that's exactly what we're going to be doing now. So you see the idea? That's why we have these different sets. So I'll show you now. Let's look at the example. This is a very intuitive example, so you can actually relate it really intuitively. The nice thing about even this example, is very easy. Actually, the results we do here are extendable to a very wide class of mechanical systems in general. Okay, so whatever we say here is not just for the pendulum; it's actually for mechanical systems in general, even though if we don't show it. I'll correct myself. Mechanical systems that are similar to it, but what is similar, that's another story. So this is the state space model of the pendulum. Okay, it should be familiar to you. So we had x1 dot is equal to x2. We had x2 dot is equal to minus some constant multiplied by x2 and some another constant multiplied by sine of x1. Okay, C1 and C2, they are just constants that are greater than 0. They don't care. Okay, in the assignment, who started solving the assignment? No one? Okay, this was one of the problems. Okay, so this is question number 3 in the assignment. Okay, so what you should have been doing in the assignment, unfortunately, okay, is that you should have started from this Lyapunov function. What does this look like? Kinetic energy, and this is potential energy. Exactly. The C1, just to remind you, actually the first time I did not introduce to you the C1 and C2 like that. They were actually including the mass and the length, and they had the gravity. And the damping friction. This term C2 was actually B, which is the damping coefficient, divided by ml squared, right? And this C1 was equal to G divided by L. If G is positive and L is positive and B is positive, physically, they have to be, then you see that C1 and C2, they have to be constant numbers. Just, positive constant numbers. We just read them like that. Okay.
Positive or negative constant numbers?
Sorry?
Negative constant numbers.
Positive?
Positive or negative constant?
Positive. We have the minuses outside, so they have to be positive. Okay. And actually, this is that's correct. So this is half x2 squared, and this is C1 1 minus cosine x1. So x1 here, doesn't you remember in this example what is x1 and what is x2 physically? Theta, exactly. So x1 is theta and x2 is theta dot, exactly. So the angular velocity. So you see here, I have something like half angular velocity squared. So it's just missing, something like a j term. And this actually j is just ml squared. This is just here, is 1 for the dimensionalization. And here we had something like it's like mgh, mg with the height, and the height of the pendulum, would be something like mg. And then you have the height. It was 1 minus cosine theta. It's actually very easy to check for yourself that this is really the kinetic and potential energy. But even though if you don't physically you don't think about it, take this as just some mathematical function, given like this. Can we show that it's positive definite? So first, this term is quadratic, so immediately it's positive definite. What about this term? First of all, the first thing you need to check out always is that V of the equilibrium point you're interested in is actually 0. We need to be 0 at that point and then positive everywhere. So it's 0 at that point clearly, because if I have x2 is equal to 0 and cosine x1 is equal to 0, then cosine 0 is 1. So 1 minus 1 is 0, and then I have here 0, then I have 0. And it's positive everywhere, excluding this equilibrium point 0 and 0, right? Make sense? What about remember we had 2 equilibrium points, right? What about the other equilibrium point? Does anyone remember what it was? Pi and 0. So if I put here pi and 0, then I get here 0. And if I put here pi, 1 minus negative 1, it's 1 minus negative 1, then I'd have the 2. So V of x, you see, at the top position is 2, and at the bottom position is 0. And everywhere else it is positive. Okay? So this is how the V of x looks like. You can just plot it, Just take all values of x1 and x2 and just plot them, and you find it's a function that's 0 only at the equilibrium point 0, 0, and it's positive everywhere, and the maximum number it reaches is just 2 at the equilibrium point pi and 0. Make sense?
I think this kind
It's a function of x, which means it's defined everywhere in the state space. Whether it's positive or negative, positive definite or semi-definite depends on what point you're looking at.
But
That's
here, for example, if we define it like this, يعني it will be v dot here less than and equal to 0. And
wait about the v dot. No. I see what your point. Using it to evaluate the stability, you can only do that for the point that makes it 0. You see?
for the point,
That makes it 0. In order to use the Lyapunov function to check whether the equilibrium point is stable, it has to satisfy 0 at that equilibrium point.
so it's not satisfied at the upper one.
Then I cannot use it.
So here it is defined only at the lower part.
It's defined everywhere, but to use it to assess the stability, we can use it only for the lower part, because this is the point that makes it 0.
Okay. So if I wanted to make it for the upper part, so I need here to make the x negative y, right?
You need to shift it, maybe. Exactly. You can add a constant. You can just add -2 here, right? But still, this doesn't tell you about the stability stuff.
So this condition, what is it? If this is the candidate for everything, so this condition to satisfy what?
So two things. Okay. V is what is the values that it takes in the state space? What is the minimum and the maximum value as a function?
From 0 to 2 pi.
No, that's not correct.
For, as x?
V. I'm talking about the V, the function. Same. V is a function that eats x and gives you r, real number. So if I give it all points in x, I give it all of the x's, what is the range exactly of the V? What is the minimum and maximum?
From 0 to infinity?
No, that's not correct.
To maximum.
So this part, exactly, it goes to infinity, that's correct. Yes, I agree. But this part,
From 0
it goes from 0 to 2, exactly. So that's correct. So this part alone goes from 0 to 2, and this part alone goes from 0 to infinity. This plot, so I advise you actually to go home and plot this actually. You can plot it in a 2D plot, in a 3D plot. You'll find that in the x2 direction, it goes up to infinity. But in the x1 direction, it has a plateau at 2. Do you imagine it?
Yes.
Okay, because of this term. So the more I go in terms of x1 equal to infinity, I'll find I never exceed the 2. You know why? Can anyone guess why? Because actually the x1 doesn't go from minus infinity to infinity in the real life. In the physical system, it goes only from minus pi to pi. You remember what's actually the state space? How does it look like?
Yes.
It's actually a cylinder only.
Yes.
Remember? In the x1 direction, I have from minus pi to pi, so that's a circle. And then I have, in the x2 direction, I have an infinite, I have an r. And thus the function is defined on that space. It's a function on that manifold. So when you're plotting it, you have to plot the x1 from minus pi to pi. And in that region, what do you see?
0 to 2.
You see a function that only goes from 0 to 2. And what about in the other direction? You can go from minus infinity to infinity. So from 0 to infinity, absolutely, because of the square. Okay. So this function, in the end, is positive definite. You all agree? Is it that's another question. Is it radially unbounded from what I just said? Is this function radially unbounded? You remember what does the radially unbounded mean intuitively? Radially unbounded. Let me show you the definition again. So this was the definition of a radially unbounded function. The v of x goes to infinity as a function as the x goes away from x star, but this norm actually means that in all directions. From what I just described, if you move in the x2 direction, if I move in the x2 direction to infinity, you'll find that the v goes to infinity. But if I move in the x1 direction, I'll find that it will maximum reach 2. Okay? Make sense? So it's actually not radially unbounded. So I cannot use this function to actually check global asymptotic stability. Okay, make sense? Is that clear? Now what you need to do, you will do it in the assignment. You take this v, calculate the gradient of it, and then multiply it by x1 dot and x2 dot. So you take the partial derivative of this with respect to x1, multiply by x1 dot, which is x2, calculate the gradient of this function, so the partial derivative of this function with respect to x2, multiply by x2 dot, sum these two terms. You should show in the end that you get this, that v dot is equal to minus c2 multiplied by x2 squared, which is negative semi-definite. Why? From those who attended last time, why is this negative semi-definite? If you look at it intuitively, you say that, you know what, it's always negative, right? Because it doesn't depend on x1, which means that x1 can take a positive value and still v dot, and x2 takes 0, and then x dot is equal to 0. So you see, it has to depend on both x1 and x2 so that you can check negative definiteness. Another way to check it actually is to rewrite it into a matrix, a Hessian form. If you remember, you'll find that there will be 0 multiplied by x1, and there will be c2 multiplied by x2 in this Hessian matrix, which means that actually the eigenvalues are 0 and c2 in this example, which means that actually it's not negative definite. The Hessian is not negative definite matrix, which means that the function is not negative definite. So this is what you conclude from Lyapunov's method, that the equilibrium point 0 and 0, which is the downward position of the pendulum, is only stable according to Lyapunov's direct method. Physically, when you start, C2 here, by the way, it was the damping coefficient divided by ml squared. The damping coefficient, if it was 0, then we would get that v dot is equal to exactly 0, which means that it is truly actually stable, right? You remember what I showed you in the animation? You start from some initial condition and you keep on just oscillating back and forth forever because there is no damping. If you have a damping coefficient, you expect actually that you start anywhere in the state space, away from, of course, the top position. You start from like here. What happens? You just keep on oscillating. Even if it takes a lot of time, eventually you will just go to the equilibrium point. So physically, we know that the equilibrium point is actually asymptotically stable, but using the total energy of the system, we cannot show that. How can we do? How can we move forward? I'll show you next. Yes, Naman.
We are calling that if it comes down and
Yeah.
it keeps doing like this is stable.
No, what I'm saying is that if there is no damping coefficient and you take the pendulum, you bring it up,
It will keep going.
it will start from this point and then will keep on going to the other side and then come back to the same point and so on. This is stable.
And then what we will call this situation where we have damping, it swings and stops.
Eventually, when it stops, this is called asymptotically stable. Even if it takes forever. By forever,
Forever to reach that.
forever to reach that point. If it's very small, that if the damping coefficient is 0.000001,
Like in the phase plot, it down.
and then you let the simulation run for 2 hours, and then after that 2 hours, it just
It comes down.
exactly.
Then it is asymptotically stable.
Then it's called asymptotically stable.
And if that circle keeps itself
Forever,
forever,
that's stable.
that's stable.
That's stable because it did not blow up. Right? Stable means not unstable.
When we are designing any controller for
Yeah.
as a matter of fact, what would we prefer it to be? Naturally, we would want it to become asymptotically stable, right?
As stable as fast as possible. This is always the requirement, right? You need to.
Asymptotic, not stable.
No, of course, asymptotic, yeah, exactly. It depends on when you're saying in general. I'm saying in the most common cases.
Like for example, if you have a robot or drone and you want it to go to, for example, B position, you would want it to be asymptotically stable over there, like reach there and does not keep oscillating about its position.
Absolutely, yeah, that's
Or
correct.
Move there and stay on that particular.
That's correct,
That
yeah.
would be asymptotic.
That's asymptotic,
We
yeah.
can make a system asymptotic stable. We cannot make a system stable by stable.
If it's unstable and you make it stable, that's the best you can do. Then it's okay. Maybe that's already a requirement.
I think all the systems are asymptotically stable. Like they reach stability at the end.
Not necessarily. When you go to nonlinear dynamics, things can be very complicated. You can have something that you can actually have for in nonlinear systems, something called actually limit cycle. Limit cycles are actually something that they keep on oscillating forever.
And also hysteresis contributes to this.
And hysteresis also plays a role on some things can get nasty.
When can we say that the pendulum is unstable?
You never say this. Even what I just said now, I cannot say that even the pendulum is asymptotically stable. What is the correct phrasing of of the question? Why is Muhammad's question not correct in itself?
At a particular point.
Exactly. Stability is for equilibrium points, not for the system. This system, we know from beginning it has two equilibrium points, so I can talk about this equilibrium point on its own, this equilibrium point on its own. This function that we chose is only valid to check the stability of this equilibrium point alone, similar to what Muhammad was talking about, because it's only 0 at that point, not at the other one.
For one of these or both of these?
Only for this one it's 0.
Green one.
For the green one, not for the purple one.
And for purple, it will be a different Lyapunov function then?
No, plug it in. Plug in 0 for x2, what do you get? You get 0 in this term. And plug in here pi, what do you get? You get 2. 2 multiplied by c1. Assume the c1 is just 1. So you just get 2. So that's the value. Can you use it for the Lyapunov function? That's the first thing of Lyapunov's theory was v at the equilibrium point is 0.
So this Lyapunov function does not work for that equilibrium?
Exactly. One easy fix, you might say, you know what? I'm going to actually minus 2 here, such that the equilibrium point is 0 at that point. So we satisfied this one. But is it positive everywhere else? No, it then became it negative. Then it's not even a Lyapunov function. So you remember there was a discussion a while ago when we talked about, can we use Lyapunov function to actually show instability? Usually, starting like this, usually it will fail if you start in this way. There are other theorems if you want to do it. One of them actually is just Lyapunov's indirect method. And that's actually, we already showed it. I think it was in the slides. You can actually take this equilibrium. Well, actually, we already did it, I think. Oh, no. Actually, it was in the supplementary material. Calculate the Jacobian of this system. Evaluate it at this equilibrium point. You can show that the top equilibrium point actually has a positive eigenvalue, which means it's unstable, exactly, by Lyapunov's indirect method. So now let's look at Lassalle's invariance principle and how can we move further. And this is how you do it. So first, we're going to be choosing that the set omega that includes the equilibrium point is the whole state space. So we don't need to worry about the omega. It's just everywhere in the state space. Now let's define the set of R, which consists of all of the set in the omega, which is the state space, that have the Lyapunov function derivative equal to 0. Remember, we calculated already the v dot. What was it equal to? What we just calculated now. It is equal to minus c2 x2 squared, which means that the set R that has v dot equal to 0 is what? Is x2 is the set of all points x1 and x2 in the state space that have x2 equal to 0. Imagine that x1 and x2, just for simplicity, is just the plane R, the R2. So I have x1 from minus infinity to infinity and x2 from minus infinity to infinity. Which subspace we're talking about here? X2 equal to 0 is what? The horizontal line, the x-axis, The x-axis is always it's all of the points that have x2 equal to 0. Make sense? So this is what this is telling you. So R is simply the x-axis, the horizontal axis of the state space. Make sense? So, are we done yet? No, we need to check what in R? The largest invariant set. So the M. So here, the points that form the invariant set are the points that have x2 equal to 0. How do we find actually these equilibrium points? We go now to the dynamics back. If we put here x2 equal to 0, it means that x2 dot is also equal to 0, right? Because inside of this invariant set, if I start there, I stay there. So I have x2 equal to 0 and I have x2 dot is equal to 0. What are we left with?
And x1 dot will also be 0.
And the x1 dot will be also equal to 0. What are we left with? sine of x1 equal to 0. Sine of x1 equal to 0, this is simply the set that makes M. So I have x2 equal to 0 and sine x1 equal to 0. But sine x1 equal to 0, I can actually solve for it. What are all of the values that satisfy sine x1 equal to 0? For x1, they are 0 and the pi. Are we going to go back to the k pi? We said, for the x itself is actually from minus pi to pi. So inside of this range, it's only 0 and pi. So I have, in the end, how many points are inside of M? I have 2 points, which are already the equilibrium points. The first one was x2 equal to 0, and x1 is equal to 0. Because that satisfies x1 equal sine x1 equal to 0. And the other one is that x2 is equal to 0 and x1 is equal to pi. Take these 2 equilibrium points and then take the union of them, or in other words, just put them into one set. We call this M. Done.
Is there another conclusion after this?
In this way, can we conclude anything?
We should conclude that locally asymptotically stable.
No. What you should conclude from here is that if I start at the equilibrium points, I'm going to stay there, but that's already the definition of the invariance set. But also, what this says is that if you start in the region omega, okay, I'm going to go either to this equilibrium point or that to the equilibrium point. I'm going to go to one of these invariant sets.
It should be omega L, isn't it?
Omega here is the whole state space, right? I'm not restricting it. So what I'm saying is that one of these 2 equilibrium points, actually I'm going to go to. Is this enough to actually conclude that we have asymptotic stability? This is nothing. Right? It says that you have 2 equilibrium points. One of them you're going to go to. That's what Salle's invariance principle tells you. So it's not enough. Without specifying which one is stable or unstable. Remember, there was another condition that we needed to actually satisfy to actually conclude the asymptotic stability. What was it? Let me go take you back. So here. So what did we need to continue? So we stopped here. So we stopped saying that M is the largest invariant set in it. We found M, we found R, and based on our omega that we chose, that actually it was the whole state space. So, and we finished. In order to conclude the asymptotic stability, we needed one extra condition. What was it?
To infinity.
No, that's not the radial unboundedness. No. This condition. If M contains only the equilibrium point that we want, so it only contains one equilibrium point, then we can conclude that we're going to be going to that M, and that M already is the equilibrium point we want, so we can conclude asymptotic stability. But the M that we calculated here included 2. What to do next?
But it includes 2 equilibrium points.
It includes more points, exactly. Not just the one that we want. Restrict the omega, exactly. You can repeat the whole procedure by going back to the omega. No one told you to start with the whole state space. Remember, actually, so how do we actually restrict the omega? Take a look at the Lyapunov function that you chose, v of x. Remember, what are the values that we found? It was going from what to what? From 0 to 2. Okay. It is 2 exactly where? At what point? At the pi. At x1 equal to pi, it was exactly equal to. And when I included v of x less than or equal to 2, okay, in the x1 direction, then we included that point. What should we do to restrict it? Remove the 2. To look at, so let's choose that. We're going to be considering the omega to be equal to omega 2c1. What is this 2c1? 2c1 is simply, so omega 2c1, this is the name. So omega, this whole red object, is actually the name of a set. It is the set of all points in the state space that satisfy V of x is less than 2C1. So if C1 is equal to 1, as we know the simplification, then you simply say that V of x is less than 2, strictly less than 2, does not include the 2. Make sense? Inside of this set, now we're going to be refining the R. Yes, question.
V now has a 2D and how can I say it? It's in 2D, right?
That's right.
Because it has two.
It's a function of two variables, yes.
Two variables, okay. So if you put it, if it's just a inequality of one variable, so it's restricting it as a circle, right? Restricting
So what we're going to be doing here is that we said that in the x2 direction it goes to infinity, right?
Yeah.
We don't care.
We don't care, yeah.
We're just going to cut it
That's what I'm asking.
at 2. That's exactly what it says. At the 2C1 variable.
Yeah, but shouldn't it be unrestricted in the x2, unrestricted only in the x1?
Can we do that? Maybe we can refine the omega to be that way. Yeah, maybe we can do that. I don't know how. I don't know how we do actually define the set. Maybe think about it. Think about it. I don't know.
Can you make it as sets? Yeah. One.
I think what this doing is just trim.
Yeah, it's trimming.
It's just trimming the whole the whole function. This is actually much better with pictures. Actually, maybe I should have prepared pictures here. Okay.
It is just a plane on top of that.
So the v of x, if you plot it, you'll find in the x1 direction from minus pi to pi, it just starts from 0 and goes to 2. And then in the x2 direction, it goes from 0 to infinity in both directions. It's a parabola in that direction. What we're going to be doing is that we're just going to cut.
Bring the plane and cut everything above.
Exactly above 2. We remove it and then look only at the omega that's less than. That includes the v of x to be less than 2. Okay. It's actually better to with pictures. So maybe if someone send me an email, maybe I can prepare them. Okay. Or better if you prepare it yourself. Maybe have a small bonus. Okay. So that's the omega. Okay. So this is how we define the omega. Inside of this omega now, we can find the new R. So the R is, again, the same set of all x2 equal to 0. But now you see we're not looking in terms of the whole state space. We're only looking at this new set. And the largest invariant set inside of this new omega is only the equilibrium point. How do we know that? We're continuing the analysis, and we're not starting from at this point. We're already from the previous slide. We already checked that if I have all of the state space as the omega, I get the two equilibrium points. I know that the equilibrium point V at this one is equal to 2. So when I exclude, the V is equal to 2, then I exclude it from this analysis. But then we're left with this one. Okay? And therefore, using Lassalle's invariance principle, every solution originating in this omega region will tend to the equilibrium point as t tends to infinity. And therefore, you can conclude that this is locally asymptotically stable. These are two slides of a lot of analysis. Usually, you actually, you think about it and you just do it once. This whole thing, if you read a lot of papers, you'll find that this is actually just one line usually in a paper. Just one line. You don't need to show it. You usually say that, I conclude that, for example, you say that, I reach this result, and by Lassalle's invariance principle, I can always, show that it's asymptotically stable. Usually, it's very easy to do all of these checks. You do it on the side, and you just conclude the result. Okay? Because it's this whole idea of, this whole analysis is just, sometimes trivial, and you just repeat it again and again. So that's what I mentioned about what we're doing here is actually applicable to a lot of a much bigger class of mechanical systems. Okay. Yes.
If we excluded 0, the M will include also the two equilibrium points?
If we excluded a V equals 0, but then the V is less than what? You see? You're thinking about a positive definite function. So it starts at 0 and goes up. It's not that, there's nothing below. That's the whole idea of the Lyapunov function. It starts from a positive definite function. So start at 0 and go up. You're always looking at a function that has this bowel shape. That's the whole essence of Lyapunov theory.
So we may exclude something above, but
not the 0 itself, exactly. Okay. Now I'll show you actually a little bit of, one second. second. Okay. Yeah, actually there was some stuff here. Yeah. Okay, so that's already what we discussed. I'll tell you a little bit of intuition. That remember when physically when we said that if I start the pendulum in the upright position, right? What happens exactly in the right upright position? It will stay there. And if I start in the down position, stays there. If I start anywhere in between, it will go to the down position. That's the physical system, right? You all agree? No doubt about it. From what we just said now, the set omega 2c1, what does it include in all of this, state space? Which points does it include in the circle, in the x1?
Should be all except this point.
Exactly. It includes all of the points. Okay, so I now have, so physically, we said that if I start anywhere, I will go down. And that's exactly what we did. Anywhere except the top position is actually this omega 2c1. You see? So that's exactly what omega 2c1 represents. It represents all of the points except the one on the top. But here we're thinking in terms of a state space, x1 and x2. And that's why we actually also have different velocities. So I can start, for example, on this position, but I can get a nudge, right? Okay. And so you can start like this and then hit it. Or start and don't give it any hit, right? Or even start like this and give it a hit on the other side. So that you have different velocities that positive or negative or zero. So that's the x2 direction. Yes.
I have a side question.
Yeah.
For example, what in this whole state space and maths we have seen, other than phase diagram,
Yeah.
phase plot, what tells us or makes us see that like this point is not going to be the like point where it can finally come. Only the down point can be the one where it can finally come.
So I'll rephrase the question to make sure I understood it. So from what we discussed so far, or we're talking about the phase space?
No, what we discussed.
What we just discussed right now. And what we discussed so far, what made us see that the top point, we will not converge to it.
Yes.
First of all, it's not included in our analysis.
Because of that. Right?
Because of this restriction that we did. So in this slide, in this omega 2c1, the point on the top is not included.
That particular point.
That particular point. Why? Because at that point, the v of x is equal to 2, c1. Go back here.
Yes.
So the v, if you plug in it, the equilibrium point 0 and 0, you get 0. If you plug in this equilibrium point, you get 2c1. So v, if I say that I don't want to look at any v that's greater than c1, sorry, greater than or equal c1,
Greater than 2 or equal to
2c1. The 2 here, when we said assume c1 is equal to 1.
Like an example, we did C1 equal to 1.
That's exactly. Then we're talking about the 2. But in general, the c1 can be something else. Okay? So you have 2c1. In that case, if you say, I don't want to take the points that have 2c1 or greater, then you've already excluded that point.
So
That's the omega now.
So that was something we knew from our previous judgment or previous physical analysis.
No, it's tightly related to the physical analysis, but here we're not using it. All what we did is simply just math here. Just, pen and paper. I computed the V at the equilibrium points and I checked them out.
Okay. But that equilibrium point came from our previous analysis.
The equilibrium point, the two equilibrium points came from the system dynamics without any physics. Remember when we said, what's actually the definition of an equilibrium point? x1 dot and x2 dot is equal to 0. And we calculated them. It was in another old lecture.
Yes, we calculated.
Remember? And we got these two equilibrium points.
Yes.
But we don't know which is stable and which is unstable and which is asymptotically stable and so on. We don't know. All what we did so far is to actually check that this one is we showed stability alone by Lyapunov's direct method. This is this slide. And we were not able to show with this Lyapunov function asymptotic stability. But when we used Salle's invariance principle, we were able to do that. Clear? Okay, so that's it for Salle's invariance principle. This is very, we can use it in the same way in different, different scenarios. The only thing that will differ is that you need just to, analyze the system that you have. We're going to come back to that later when we go to the manipulated equation and when we come to the geometric control on SO3. Okay, so we're going to come back to that Salle invariance principle in a different setting. But for now, that's just the abstract theorem and one example on it. In the remaining time, let's look at PD control on R3. Okay, so this should be I'll go very quickly on this because this is just, I want to show you a different way of looking at what you already know. This is simple PD, so that's, bachelor stuff. And let's look at the point mass. So the point mass in R3, so this is a prototypical example. We just have the rate of change of position is equal to velocity. Rate of change of velocity is equal to 1 divided by the mass multiplied by u. U here is the control force that you apply to this point mass. So that's the simple system. And we can rewrite it in terms of at state space, not in terms of psi and v, as what we usually did. We're going to be writing in terms of psi and p. Remember I mentioned something about using positions and momenta several times. This is just another example of it. Okay? So psi dot is equal to v, and v itself is actually p divided by m, right? And p dot, the rate of change of momentum, is equal to u, Newton's law. Rate of change of momentum is equal to force, that's this equation, and the rate of change of position is equal to velocity. Okay, make sense? Here, v and psi and u are all R3. Everything is vectors. Okay, everything is just 3 numbers, and these are the state space model.
Vector or tuple?
Sorry?
Vector or tuple?
Doesn't matter. Let's work with the standard Rn. Forget about the geometry for now. Okay, next lecture, inshallah, we'll come back. So,
Why you modify the second state
as momentum, not v. You'll see in this example it will be exactly the same, nothing will happen. When we go to a more complicated stuff like doing SE3 and SO3, this will pay back. Okay? You'll see why then, inshallah. What is the total energy of the system? The total energy of the system is simply, this is a point mass and it's moving around. We don't have any potential energy, we just have kinetic energy. Okay? So assume there is no gravity in this example. So the total energy is simply half mv squared, or as a vector it's half mv transpose v, or written in terms of our state that we chose is 1 over 2m p transpose p. So you can actually check at home that these are the same. Okay, one another. Okay.
Again, why you didn't add here potential?
Just for simplicity. Okay.
But
You can have the gravity. Treating the gravity is what we want to do is now just take the point mass and make it go to somewhere you want. As easy as this. So no gravity. Okay? The gravity will come later in more physical examples. So our control objective for this simple, very, very simple toy problem is that we want to stabilize it at a desired state. The desired state is simply velocity is equal to 0 and position is equal to some desired value. So I start, we have a point mass in 3D. I want it to move from here to go from here. Okay? Or go here, or go here. So this is the desired position. And I want it to go and do what? And stop. So it's a stabilization problem. Make sense? How do we design a PD controller? So I designed the error function to be psi minus psi d. It's an R3. Then the u would be simply some constant matrix, kp, multiplied by the error, e psi, and another constant matrix, kd, multiplied by the error dot. And since the error itself is psi minus psi d, so I have this is the first variable. And we said that the psi d actually is just a constant. I go there and I stop. So the error dot is simply psi dot, and the psi dot is simply v. So this is the total expression for our control. And you see, actually you can think about it. This is the u. Psi and v are the two states. Actually v, we said that p is actually our state, but v is actually p over m. So you can go back and forth, so it's very easy. So actually this is in the end the whole equation, which is gamma of x. You remember when we said that the controller is usually some function of x? This is the proof of it. Okay. Kp and kd, they have to be positive definite gains. They have to be positive gains. You cannot choose them negative definite. Okay, and we'll see why later. But it makes sense intuitively. Take your controller, plug it in the dynamics. You get this system that looks like this. What is this called now? This is called the closed loop system. Okay, so you see, Actually, this is f of x plus g, but instead of the u, now we have gamma of x. And this is simply the closed loop system. It's something that has psi and p as the states. So this is psi, and this is the v here is there. And the v is simply p over m. So I can just remove the v and put p over m there. Okay. Later we're going to be showing that this is actually asymptotically stable. But the way you do it, actually, this is a linear system, right? Yeah. So actually, this is exactly like, you can rewrite it into A minus BK form. And you can take this A minus BK matrix, and you can check what the eigenvalues of it, and you can show that it's stable. So this is usually what you do in linear control. Okay? But we're going to keep it like this, and we're going to be treating it as a general nonlinear system, even though it's just linear. Okay? Make sense?
Yes.
PD control. Any questions? Done.
Why, I have a question here, like, why you have like a negative sign for
Here.
the gains?
For the gains. The gains are positive,
Okay.
and the minus sign, okay, is in the controller itself. We say the controller is equal to minus kp multiplied by the error, minus kd multiplied by that error. In case, there are other ways how to formulate it. We could have said that the u is equal to positive kp minus multiplied by this, plus kd multiplied by that. And we could have said that kp and kd are negative.
This is based on
Convention.
direct and reversible?
No. It's just a convention. Okay? Another way we could have done it is that, and this is also another way you might have seen that, we could have said that this is kp and kd without the minuses. We could have said that kp and kd, they are positive. No, they are positive. But the error itself, we could have defined it as desired minus actual. You see here how we defined it? It's actually actual minus desired. So this is maybe the confusion that you have, right? Okay.
I think the last convention, this is the most common one.
The last one is the most common one. Yeah, you say that the PD is simply k multiplied by the error plus another k multiplied by the error dot, and the error itself is desired minus actual. We do it this way, and you'll see later why. Okay? Make sense? Take the same idea, and I'll give you a very simple problem, okay, which is a PD controller on SO3. Okay, so we're going to take a typical example on SO3, a satellite problem. Okay, so the satellite problem, was it mentioned in the assignment? I don't think so, right? Sorry, in one of the lectures, we had the MAV problem, the UAV on SA3. Okay? We can redefine another example, instead of H and V, instead of H and the twist, we can just make it simply, forget about the translation and make it into R and omega. Okay? And then you don't have a drone moving in space, you just have a satellite, trying to orient itself. Okay? We're gonna come back to the equation of motion later. But this satellite example, by the way, is in the supplementary homework. You find that there are some extra slides on the indirect method. That's supplementary, so you study it if you want, but it's not included in the exam. But you'll find there, a satellite example if you want to really have another example mechanical system. We're gonna come back to that later next lecture, inshallah. Now, I would like you to design a controller for this system. So the first thing that you do, and I'll tell you, do it a PD controller, nothing fancy. Just stabilize the satellite instead of having any orientation to have some desired orientation. You want it like this or like that or like this or like that. Makes sense? And you want the velocity to be 0. It's exactly the same, right? So we just went from a point mass to a rigid body rotation. And now you say, okay, yes, so minus kp multiplied by the error in the rotation minus kd multiplied by the error dot. And then you say that the error in the position is r minus r desired, right? And error in the velocity is r dot.
No, this is not belonging to the group, right?
Does it work?
I don't think so.
Can you say r minus rd? Why?
Because
Because it's
not
not
like-
belonging to the definition of this orthogonal group.
It doesn't have what?
like group.
This O3.
Vector space structure.
Vector space structure. SO3 does not have a vector space structure. And thus, I cannot say r minus r desired. Impossible. It's not defined. But these are 3 by 3 matrices, right?
Yeah.
So this is a 3 by 3 matrix and 3 by 3 matrix. Why not just say, first element minus first element, second element minus second element? Does it work?
No.
Alhamdulillah, it took us 20 lectures just to convince you of that, okay? So R minus R desired is not allowed. So this is an error on SE3. But even the E dot itself is actually tangent, a vector in the tangent space. So I cannot just, sum it to something that's in the, I don't know where this is, but it doesn't even match. But even worse than that, the U itself is actually a torque, which is a covector. No, it's a covector. It's just 3 numbers, but they belong to a covector. They have a covector nature. So how do we go from the R? So the same elements are exactly what we're going to be using. So we do have an R. We do have an actual R that the system has, that we maybe measure with some sensor. And we have an R desired that we want to go to. And we have an R dot. Okay, so the rate of change of this, R. We also have the omega, and we know actually the omega and the R dot, they are, isomorphic to each other. So we can use that information, that R dot is equal to R multiplied by omega tilde, the skew-symmetric form of the omega. And how can we use this stuff so that in the end we get 3 numbers, which are the torque. And then the torque you can apply to the satellite, and then it will make it work. We'll see. The same stuff that we said here holds also for a general UAV, or for a general rigid body. The only difference is that instead of SO3 and R3, you get SE3 and SE3 and R6. You have the H and the whole twist. And everything is exactly the same. You see, we're going to still have, if I have a desired pose and an actual pose, how would I make the drone go from this pose to that pose? So that's the H minus H desired, still not defined in SA3. The H dot, another tangent vector, another tangent space. And what we get as an output, as the control, is what? R6 star. And what will it be? What do you call it? If these are the torques, there it will be what? The wrench. Exactly. And then this wrench, let's say, for example, this was a UAV example. You have another problem now, which is how do you convert this wrench to the individual thrusts of the propellers? And this is called the control allocation problem. That's another story. Okay?
Do the reverse of what we did in the project of converting that wrenches of propellers to...
Absolutely. Absolutely. Excellent point, Norman. Yes, absolutely. That's exactly what you did, opposite what you did in the assignment. The assignment was individual wrenches, convert them to the total one. Now, usually how we do the control here is that you control the UAV as just a single rigid body, and then you take the wrench that you have and you invert it. Sometimes the map is easy. All of the projects that you have, okay, they had an easy invertible map because you just have a fully activated UAV, which means that the map from the wrenches to the individual propellers are just 6x6 matrix, and it's invertible, so that's easy to do. In general, it's not.
For quad rotor, it will be not that simple.
For quad rotor, it's easy also because you have actually not 6 inputs. You don't have a control wrench.
No, but it is underactuated, no?
It's underactuated, which means that I'm not actuating the force in the X and the Y, in the body frame. So I only left with 4, and I have 4 propellers, so it's still invertible. That's exactly the assignment.
That is why it does not move like this.
That's why it does not move like, absolutely, yes. So, linear algebra fails at that step. Okay?
So how can we solve this?
Next lecture, inshallah. Okay? So we'll stop here.
The motivation.
Okay? That's the motivation, exactly. Okay? So PD control will fail here. Okay? I was supposed actually to go a little bit into, just to introduce a little bit, but let's leave that for Tuesday, inshallah. Okay? So this part, we're going to move to Tuesday. See you then, inshallah. Assalamu alaikum.